It's recording.
Okay. Hello, teacher. Today we will be presenting about our math assignment project. Next slide, please. So through this project, we will be solving questions related to finding linear model using linear regression, determining the rate using differentiation, and deriving the velocity using differentiation.
Good morning, everyone. Today I'll be presenting how to solve a problem related to carbon dioxide levels in the atmosphere. The data in Table 1 represents the average CO2 levels recorded from 1972 to 1990. Basically, we are here to predict the CO2 levels from the year 1987 and estimate the levels for 2005. So we're here also to determine when the CO2 level will exceed 400 ppm. To solve this, we need to recall the basics of linear regression, where we use the equation y equals mx plus c. As we know, y indicates the CO2 level in ppm. The X is representing the year, and the C is basically the y-intercept.
So from the previous slide, we know that the graph that we are plotting, which is the linear model of atmospheric CO2 levels from 1972 to 1990, the y-axis represents the CO2 level in ppm, and the x-axis represents the year. So from the graph, we can find the gradient, which is represented by m, using 2 points randomly, and then using the formula y2 minus y1 over x2 minus x1, which would be giving us 1.49667. After finding the gradient, we can sub it into the equation and use another random point and sub it into y equals mx plus c to solve for c, which would be negative 2624.827. After finding the equation of the CO2 level over the years, we can apply linear regression, substitute the gradient and the y-intercept into y equals mx plus c, and we would get y equals to 1.497x minus 2624.8, where m represents the slope, which is 1.497, and c represents the y-intercept, which is negative 2624.8. Next slide, please.
So as we look back to our equation, where y equals to 1.497x minus 2624.827, y is the carbon dioxide level in ppm, and x the year. This equation model represents the change in carbon dioxide level over time. To calculate the carbon dioxide level for year 1987 and year 2005, we substitute the x equals to 1987 into our equation. We'll simplify this and we get carbon dioxide level around 349.712 ppm. And for 2005, we substitute into our equation as well. We got approximately 376.658 ppm carbon dioxide level. And to determine when will the carbon dioxide level will exceed 400 ppm, we substitute it into our y value, and we'll get x value around 2020.57, which will be in year 2021, when the carbon dioxide level will exceed 400 ppm. Thank you. Next.
So in question 2, we are given the conical tank, which is we know that the conical tank is being filled with water at a rate of 30 cm cubed per second, and the radius at the top of the tank is given as 10 cm and the height is 20 cm, and we are supposed to determine the rate at the water level is rising when the water is 10 cm deep. So we can use the volume formula, which is 1 over 3 pi r square h, and then differentiate the following. Next slide, please.
Hello everyone. Today's I'm gonna walk you guys through the solving the problem involving the conical tank being filled with water. So the question is asking about the rate of the water rising when the water is 10 centimeter deep. So first of all, we need to understand the geometry. We need to know the conical tank is shaped like cone, and we need to know the formula of the volume of the cone. And also the radius of the conical tank is half the height of the conical tank. So we're gonna replace radius with h by 2 in order to make the solving step way easier. And after that, I'm gonna find the volume of the cone from the equations of one that into pi r square h. And then I'm gonna substitute with h by 2 and solve it, and I got like pi by 12 into h cubed. Next slide, please. Now we're gonna differentiate the volume of the conical tank with respect to h, and then we got like pi by 4 into h squared. In this case, in this step, we have to substitute h with 10 because in this step we're gonna get like confused and then making mistakes because at first the question stated like the volume of the height of the conical tank is like 20 centimeter, and now we have to substitute h with 10 because the question is only asking about the rate of the water rising when the water is like 10 centimeter deep. And then we have like 25 pi. From the way I've solved it, like we have to find like dh by dt, right? So we have to make sure the dh is always at the numerator and dt is always at the denominator. So as I look at what I already found, and I realized that I already found the dv by dh. So to make sure dv at the top, I use it upside down. And then the questions already give us a dv by dt for the value of that d. So I solve all of them, and I got like 0.382 centimeter per second as a final answer. Thank you.
Now I'm going to walk you through the question in question 3. First and foremost, the purpose of the model is to show the modeling of blood flow in a realistic way. With that being said, instead of just assuming the blood flow moves at a fixed rate, this model dt equals to 20 plus 5 sine times 7.85 t times t captures both the steady or average speed of blood flow, the pulsatile variation due to the heartbeat, which is the up and down rhythm that slightly speeds up and slows down the blood. Next slide, please. Now we're going to break down the distance model. First and foremost, the 20 in the model dt given, the term 20 represents the average velocity of blood flow, which is how fast the blood would move if it didn't fluctuate at all. It's a constant speed, so which means that even if there were no heartbeat, the blood would still move at this steady rate. Next, it has the pulsate component, which is the 5 sine times 7.85 t. The term, it adds a rhythmic variation, simulating how the heartbeat affects the blood flow. The amplitude, which is the 5, represents the strength of the pulse, extent of the fluctuation. And the angular frequency, the 7.85 radian per second, inside the sine function reflects how quickly these pulses happen. And what the question asks us to do is they're asking for the velocity of the blood based on the distance model provided. In physics, velocity is defined as rate of change of distance over time. That's mean we're looking for how quick the distance traveled by the blood changes at any given moment. But now we're in mathematics class. In mathematical terms, finding the velocity involves differentiating the distance function, which is dt, with respect to time, t. By doing this, we can see how the blood flow speed varies at any instant, taking into account for both the steady average velocity and the pulsatile changes. And why deriving the velocity is important is when you're being asked to derive the velocity provides more detailed information about the blood flow than the distance alone, while the distance function, the dt, tells us how far the blood has traveled after a certain amount of time. The velocity function, whereas the vt, will tell us how fast the blood is moving at any specific moment. Next, please.
Now we are given the distance formula where dt equals to 20 plus 5 sine 7.85 tt. T is the time, 20 is the steady average velocity in cm per second, and 5 sine 7.85 t is the part that adds a pulse effect. We want to find the velocity from this distance function. We're looking at our equation here. We have to separate into two parts to find the derivative of the distance function with respect to time t. Next slide, please. After splitting two parts, u is equals to 20 plus 5 sine 7.85 t, and derivative of u with respect to t will be 39.25 cos 7.85 t. And v equals to t, the derivative of v with respect to t would be 1. Combining these using the product rule given above, that will be 39.25 cos 7.85 t times t plus 20 plus 5 sine 7.85 t times 1. And the equation of velocity vt at any time t is 20 plus 5 sine 7.85 t plus 39.25 t cos 7.85 t. This equation gives us the instantaneous velocity at time t combining the steady base rate, the pulsing effects from the heartbeat and how it varies with time. And that concludes with our presentation. Thank you for taking time to listen, and have a nice day.